Now, first theory was Newton's corpuscular theory. So, according to Newton's corpuscular theory, light travels in the form of corpuscles. Light travels in the form of corpuscles. Okay, corpuscles. Corpuscles means they are particle. They are particle in nature. He supported the particle nature of light. So he said that size of the corpuscle will decide the color of the light. Size of the corpuscle will decide the color of the light. And now out of 5 properties of light: reflection, refraction, interference, diffraction, and polarization. There are total 5 properties of light: interference, diffraction, and polarization. Okay. So in our syllabus, they removed polarization. Earlier it was there, but from last 2 years they have deleted this polarization part now. So polarization is not there in our syllabus now. So out of these 4 in the first lesson, in the ray optics, we only studied reflection and refraction. We haven't discussed interference, diffraction, and polarization, because with ray optics they could only explain reflection and refraction. Newton could only explain reflection, refraction. But again, he failed in explaining refraction. He successfully explained reflection. He failed in explaining refraction. Where he failed? He said that the speed of light is more in denser medium than in rarer medium. He said that generally speed of light is more in air than in glass and other medium, right? That we know. But he said that speed of light is more in denser medium and less in the other medium. He said that ether is prevailing throughout the universe. But later on we came to know in the space there is no ether, nothing like that. Okay, so there the theory was discarded. Newton's corpuscular theory was discarded. With Newton, there were 2 more scientists who supported his theory. One is Max Planck, quantum theory, quantum Max Planck. In chemistry, you have studied this. That is, what is that? Planck's quantum theory. Okay, he also supported the particle nature. Even Albert Einstein also supported the particle nature of light. Okay, then in this lesson, in the previous lesson, only 2 properties were discussed. But in this lesson, there are total 5 properties. Who explained? Huygens. Huygens explained the wave nature of light. With the wave nature of light, he could explain all the 5 properties of light. He could explain all the 5 properties of light successfully. From where he started from wave motion. Wave motion concept is in grade 9. Okay, according to wave motion, what he says? Transfer of energy from one point to another point without movement of particles. Like suppose you drop a stone in the still water, what will happen? The waves will go ahead. Is it not? Waves will go like this.
Yes, sir.
To the corner, is it not? Water is not going. Only the energy is transferring from one place to another place. Same way. So this is a simple example, a transverse wave. In grade 11, we studied both transverse wave and longitudinal wave. In transverse wave, okay, if I take transverse wave, so what he says, according to this transverse wave, motion of the particle. That means if the particles are perpendicular to the direction of the propagation of the wave, if the particles are vibrating perpendicular to the direction of the propagation of the wave, then that is known as transverse wave. Is that clear? If the particles vibrate,
yes, sir,
to the direction of the propagation of the wave, then that is known as transverse wave. Is that clear? That's known as transverse wave. Is that clear? So now, so here the wave particles are not moving from one place to another place. Particles are only vibrating towards its main position, and the energy is being propagated in the forward direction. Is it not? Energy is being propagated in the forward direction. This happens in wave motion. Then comes wave front. Wave front is what? The locus of all the particles which are in the same phase, which are in same phase. Okay, which are in same phase or constant phase difference. Okay, which are in same phase or constant phase difference. Okay, which are in same phase or constant phase difference. This lesson is very, very important. Why it is important? It is completely conceptual. There is very less derivation in this. Completely conceptual. Understand, and then only you can do. If you don't understand, you cannot do this chapter. Okay, and ray optics and wave optics, for your kind information, it carries one case study and one 5 marker and one 3 marker, one 2 marker, and few 1 markers also. So be careful with these two chapters and the electromagnetic waves. It carries more marks. Don't lose any mark. And there is more drawing also. We can easily score marks because definitely you need to score. You need to draw a telescope or a microscope. Learn telescope, microscope very well, and draw the optical instruments only with the pencil. Never draw with the pen, and label it properly. Is that clear? Is that clear? So now we will go ahead with locus of all the particles which are in the same phase or constant phase difference. Now all these particles are in the all these dots. Okay, have you seen like rangoli? When in India we put rangoli, have you seen first we put the dots, is it not? Then we join the dots. Yes, have you seen rangoli anytime?
Yes, sir.
Yes, sir.
Yeah, so same thing in rangoli. What they do, they first put the dots, then they join the line. Yeah, that with the powder. That when one powder will be there with the powder, they will put the first they put the dots, then they join the lines, then they make the patterns. Is it not? Same way. These all the points are locus. Okay, these all points are said to be locus. The locus of all the particles which are in the same phase. They are all in same phase. Okay, or constant phase difference. That is known as wavefront. Okay, they are also from a fixed point. Is that clear? So now, what is phase?
Yes, sir.
Phase means it describes the state of motion and direction of a particle. Motion and direction of particle. Okay, motion and direction of particle. Please copy this one, then we'll go ahead. Okay, we'll go ahead with we'll discuss in phase, out of phase, constant phase difference. Then we'll discuss about wavefront. Okay, some more ways in which wavefront can be explained. Okay, so it describes the what is phase? It describes the state of motion and direction of a particle. State of motion and direction of a particle. Okay, so what we have here, we have in phase. Okay, we have in phase. What is in phase? Like suppose two waves are there. Like this, there are two waves like this. Like two waves are there like this. Okay, one another. Okay, so they are said to be in phase. There are two waves now. So if the phase difference between both of them is 0 degrees. Okay, phase difference is 0 degrees. That is in phase. Best example for this is what? I told you the Republic Day parade, marching of soldiers in Republic Day parade. All the soldiers are marching, so they are in phase. Now, one more way in which we can explain phase. What is phase? So we can explain in this way. Phase is, angle made with its initial position. Okay, angle made with its initial position. Angle made with its initial position is said to be phase. Okay. Now, so suppose this is the thing. So this is the angle. This is the angle. Okay. So this angle. So suppose it was supposed to start from A. Okay. So A, B, C, and D. It was supposed to start from A. So this is point P. If the particles, instead of starting at A, it started at P, then it will complete one rotation only at P, right? Is it not? When it is starting at P, to complete one rotation, it has to come back to P. Then only it will complete 2 pi radians. That is said to be phase. Okay, angle made with its initial position is said to be phase. Now, in phase, if the angle between the two waves is 0 degrees, that is in phase. Next is what? Out of phase. Out of phase means what? Phi is equal to 180 degrees. Okay. Out of phase means phi is equal to 180 degrees. So here, I'll draw here. So here, what will happen now? So this is 180 degrees. Okay. Now, third one is what? Constant phase difference. Okay. Constant phase difference. Why I am teaching this one? Because in interference, the problem is we need to teach difference, that is relation between path difference and phase difference. This is the very, very important part. So here constant phase difference means phi is equal to maybe 30 degrees or something like 30 degrees or 40 degrees, something like that. Okay, that is constant phase difference. In constant phase difference, suppose this is one wave, the second wave is like this. Okay. So this is said to be constant phase difference. Okay, one second. So we have constant phase difference. Okay. So means there is some angle between, that is leading or lagging of a wave. This we already discussed in AC currents also. When I was explaining AC current, then also I explained you about constant phase difference. Means maybe 30 degrees, 40 degrees, 50 degrees, something like that. Okay. So that is known as constant phase difference. Okay. Clear? Okay.
Yes, sir.
Yes, sir.
Okay. Okay, copy this one, then we'll go ahead. Okay, it can be 30, 40, it can be anything. Okay, it's not like mandatory, it should be only 30. I'm writing theta. Okay, better. Is that clear?
Yes, sir.
Yes, sir.
No, the black one. There it is. Copy this, then we'll go ahead. Okay, then I will teach you what is wavefront, then plane wavefront, and then spherical wavefront, cylindrical wavefront, all this I will explain. Okay.
Yes, sir.
Done, sir.
Done. Okay. Then we will discuss about plane wavefront, spherical wavefront. Before going to that, I will discuss about Huygens wave. What do you call it? Huygens wave theory. What he says. So wavefront is defined as surface of constant phase. Okay. So one more definition here for locus for wavefront. That is, it is defined as. It is defined as a surface of constant phase. Surface of constant phase. It is defined as a surface of constant phase. Okay. Now, next is Huygens principle. Okay. Next is Huygens principle. What is Huygens principle say? Huygens principle says that each point on a, or we can write one more definition. What is that? The lines perpendicular to the rays is known as wavefront. Okay. Lines perpendicular to the rays is known as wavefront. So then you got three different definitions. The locus of all the particles which are in same phase, or constant phase difference, or it is defined as a surface of constant phase, or lines perpendicular to the rays. Okay. After that we have Huygens principle. In Huygens principle, he says that each point on a wavefront becomes a source of secondary disturbance which spreads out in the medium. Okay. So first, before that, before this, I would like to go tell about the plane wavefront and spherical wavefront. Plane wavefront. What is plane wavefront? Like suppose these are the rays. Okay, these are the rays. Now, what are the wavefront? These are the wavefronts. Okay, these are the rays, and these are the wavefronts. Because these wavefronts are known as plane wavefront. Okay, this is known as plane wavefront. Next one is what? Spherical wavefront. These lines are perfect. They are not arrows. They are only lines. They are scalar quantity. Wavefront, rays are vector. Rays are vectors. Same like if you understand electric field and electric potential, same thing. If this is electric field, this is electric potential. If these are the light rays, these are the wavefronts. Is that clear? Is this clear all of you? Now,
Yes, sir.
now next one is like spherical wavefront. Like suppose this is a source. Now light rays are coming out in all the directions. Light rays are coming out in all the directions. So what will happen now? These are the rays. Okay. So these are the rays. So what will happen? This is one wavefront. Second wavefront. Third wavefront. Is that clear? Is that clear? So we have these are the rays and these are the wavefronts. These are not circular wavefronts, spherical wavefronts. Like suppose there is a candle, there is a light here. Now what happens? Light is going in all the directions. But when you say the wavefronts, this is first small wavefront, bigger wavefront, then bigger wavefront. Are you understanding? Imaginary spheres, concentric imaginary spheres.
Yes, sir.
They are known as spherical wavefront. Okay, this is plane wavefront, and this one is spherical wavefront. Is that clear? These are the rays, and these are spherical wavefronts. Is that clear? Is that clear?
Yes, sir.
Yeah. Copy this one. Then quickly we'll go to the Huygens principle. What Huygens told. Very, very important. Once you understand this, then you will be able to draw the secondary wavelets, primary wavelets. We'll discuss that. Then quickly we'll go to the reflection and refraction. If you have any doubt, please ask me. And this lesson is completely conceptual lesson. Huh? Yeah, numericals also will be there. Interference numericals will be there. Done? So I'm going ahead with the Huygens principle. Okay, clear?
Okay, sir.
Okay, so he says that in Huygens principle. In Huygens principle, each point on a wavefront becomes a source of secondary disturbance which spreads out in the medium. Okay, the first point, each point on a wavefront, becomes a source of secondary disturbance, which spreads out in the which spreads out in the median. Which spreads out in the median. Okay. Each point on a wavefront becomes a source of secondary disturbance which spreads out in the median. Okay. Now, how to explain this? See here. He tells about a first. I'll take a plane wavefront better. I will not go to the circular wavefront. I'll take a plane wavefront. Now, suppose think that these are the rays, light rays. Okay. These are the light rays. Okay. And these are the wavefronts. Okay. Clear? This is the first wavefront. Now,
Yes, sir.
these are the points. These points where they are meeting. Maybe the ray and the wavefront are meeting. I am considering this as a wavelet. Okay. I am considering this as a wavelet. Clear? Or also known as primary wavelet. Okay. Means what happens is source of secondary disturbance. Source of secondary disturbance means what? Like draw a sphere. Okay. This is second sphere. Then this is second sphere. Then, so this is the source of these points are the source of secondary disturbance. Means what? If you draw one more line, it touches the envelopes of all the spheres. It touches the envelopes of all the spheres, which makes the next wavefront. If this is the primary wavefront, okay. If this first line is primary wavefront. Okay, primary wavefront. And this will become what? Secondary wavefront. Clear? This will become secondary wavefront. And these dots are said to be the secondary wavelet. Okay. Secondary wavelet. Is that clear? This is primary wavelet.
Yes.
This is the secondary wavelet. This is primary wavefront, secondary wavelet. These spheres, these are the concentric spheres. Is that clear? So now, we will explain that. First point, what he says, each point on a wavefront becomes a source of secondary wavefront. This is source of the secondary wavefront. So first, what he will draw? He will draw the circles. Now the question is, sir, what should be the size of the circle? Means what should be the radius of the circle? Is it not? The question should be, sir, you are drawing a circle nicely here, and all the circles, when I draw a line, all the perimeter of all the circles or the envelope of all these circles will touch, all the spheres will touch, and will make a secondary wavefront. Well and good. But what should be the size of the sphere? That matters. Now, the second point, he says the point of wavefront at any point instant may be obtained by drawing a forward common envelope to all the secondary wavelets at that point. Okay, he will take a picture and send it to you in the group. Just take this picture. He's going to take a picture and sending it these points. I'm going to explain all these points. When he's asking, what explain Huygens wave theory or Huygens principle, then you have to write all these 4 points. There are 4 points here. Okay, you have to write all these points. So secondary point, okay, did you get that? Please check. So
Yes, sir, we got it.
he says in that point, he says that the point of wavefront at any point later instant may be obtained by drawing a forward common envelope to all these secondary wavelets at that instant. You have to draw a forward envelope, not the backward envelope. Keep that in the mind. No, sir, I will go backward. No, because the ray is going forward, I am also taking the forward common envelope, not going backward. Okay, that's the second point. Third point, in an isotropic medium, the energy carried by waves is transmitted equally in all the directions. Means what? Here, all this, the energy carried is by waves is transmitted equally in all directions. Okay, they are carried equally in all the directions. This, suppose, example, this is a plane wave. energy is equally transmitted. Now, suppose I want to go with circular, like this is the point source. Now I am drawing the rays. Okay, these are the rays. These are the light rays which are coming out from the which are coming out from a point. Okay, which are coming out from a point. Now I am drawing an envelope like this. Here I am drawing in. So this is what this makes the first sphere. Okay, this is also known as primary wavefront, and these dots are known as primary wavelet. Okay, these are known as primary wavelet. Now, if I draw a circle for each like this, see, I draw a circle for each of them. Keep that as a center and draw a circle for each. Okay, keep the dot as a center and draw. Then touch all of them. We get the secondary. We get the next wavefront, secondary wavefront. Is that clear? So now, in an isotropic, in the position of next is if the initial shape, position, and direction. See, energy is equally transmitted everywhere. It is equally transmitted everywhere. Now, Ashas, listen to the class. Otherwise, I will come there and slap
Yes, sir.
you. No concentration.
Yeah, sir. I just now saw that.
I thought I should not scold any child, but you people annoy me. Is it necessary to write the message now? You also, man. Okay. Now, where I was. Okay, I was in the secondary wavefront. This is the primary wavefront. This is the secondary wavefront. Okay, primary wavefront, secondary wavefront, primary wavelet, secondary wavelet. Okay, and energy is transmitted equally. Now, next is if the initial shape, if you know the initial shape. See here, it is the initial shape. This is the initial shape. If you know the initial shape, position, direction, and motion, and speed of the wavefront, then you can find out the position at a later instant by geometrical construction. Okay, by geometrical construction, just by drawing a geometrical construction. Now when people asked him, Hagen, what should be the size of the sphere, sir? You're not explaining that. Every time nicely you're explaining primary wavefront, you drew the nice spheres and you're saying envelopes. Perfect. But what should be the size of the sphere? What should be the radius of the sphere? Then he said that. Then the next question he asked is, at what time you want the next wavefront? After how much time you want the wavefront? You tell me that, he asked. Then people said, okay, 1 second. No problem. We will solve this question, he said. How it is? He said, velocity is equal to displacement by time. Very simple formula he used. Then instead of velocity, because we are working with light, light is speed of light. And what is here? X is equal to radius. Okay, X is the radius. And T is capital T. 1 second. Hello, ma'am. Now here he says C is equal to R by tau. Now immediately when when people asked him what should be the radius of the sphere, then he asked, at what time you want the next wavefront? You tell me now. Then he said, okay. Then he used the formula velocity is equal to displacement by time. C is equal to R by tau. Tau is the time. Example, instead of taking T, he took tau. Then R is equal to what? R is equal to C tau. Just multiply the speed of light with whatever the time you want, 1 nanosecond, 1 microsecond, 1 millisecond. It's up to you. You decide. Then you can draw the next. You can draw the sphere for the next one like that. Is that clear? By keeping the primary wavelet at its center. Is this clear, all of you?